All right, guys, here's the third example I gave you on the workshop that you can print out the whole workshop on mrrouse.com. And there's also more in-depth lessons on how to do this. You kind of go back. I'm jumping in towards the end right here. So if you want more background, go to mrrouse.com and look at the 11th topic, which is about kinetics. So let's take a look at this one here. Let's figure out how the concentrations change and how that changes our rate. And for the first one, let's look at A, the concentration of A. I got to find two examples where A is changing but nothing else is changing. Well, I can see 4, and the fourth one, A is changing from the other ones. So now let's find an example where the other ones are. So I'm looking at experiment 4 and number 1. Between 4 and number 1, A is changing, but B is staying the same, and C is staying the same. Therefore, the change is entirely based on A's concentration. And if we look at this, the concentration of this is doubling. When A doubled, what happened to the rate of the reaction? The rate of the reaction, so when A doubled, the concentration doubled. It's going to be raised to some power, X. What happened to the rate? The rate didn't even change. So therefore, so it stayed the same. So therefore, reactant A is a 0 order. Anything raised to the power of 0 is 1. So A is a 0 order reactant. So I'm going to put that up here. I'm going to say this is a 0 order reactant. Changing the concentration A does not change the rate of this reaction. Now let's look at B. Let's look at B. We see that it's changing here, and we want an example where C and D are not changing. I'm sorry, A and C are not changing. So here we have changing of B, and if we look here, A doesn't change. B does change, it doubles here. It doubles from here to here, and C doesn't change. So the change in this concentration is entirely based off of B. So as B doubles in concentration, B doubles, I'm going to say this is to some power Y. What happened to the rate of the reaction? So it looks like it quadrupled, but if you're not comfortable just looking at that, let's just do this. 0.48 divided by 0.12, and we have 4. It went up by 4. So when the concentration doubled, the rate of the reaction quadrupled. Therefore, Y, or 2 to what power is 4, is the second power. So B is second power, is a second order reactant. Now let's try to do the last thing with C. So we're looking at an example where C is going to change, but the other ones are not going to change. So we have a couple choices. We can see it's going to be 1 or 4, but not both, and then 2 and 3. So let's take a look here at a good example. I'm going to say, what looks like, it looks like 1 and 2. Would you guys agree? From 1 to 2, this is changing, but A stayed the same. B stayed the same, but C did change. C's changed. So I'm going to write this one out a little bit more detail here. So the concentration from it doubled. So I'm going to use the larger number on top. So I'm going to say 0.6 to 0.2. That's its change, and it's going to be to some power. I'm going to say that's a Z power. I don't know what that is yet. And it went from 0.12. I'm choosing, remember, experiment 2 over experiment 1 over 0.04. And let's just calculate that out real quick. 0.6 divided by 0.2 is 3. So the concentration changed by a magnitude of 3, and it's raised to some power. And the rate of the reaction went up. You can see that's also 3. 12 divided by 4 if we move decimal place over twice for both of them. So that's also 3. So as the concentration tripled, so did the rate of the reaction. Therefore, this is a first order reactant. 3 to the first power is still 3. So, and we said this was a second order, and this is a first order. So we can take a look at that there, and now we can write the rate law. The rate law is the rate equals K. I don't have to include A because the concentration of A doesn't make a difference. We saw that in the first one. As we doubled A, it didn't change the rate of this reaction. So we don't need to worry about A in the law, because as long as A is available, the reaction will occur, but it doesn't change the rate of the reaction. So times b squared times c, and c is first order, so it's just like that. So that's our rate law. Now let's solve for k. Let's solve for k. Rearranging this, I could say k equals the rate over b squared times c, b squared c. And I'm going to choose the fourth experiment to actually plug in values for that. So k equals, the rate is 0.04, and it's important to put those units in there, and that is molarity per second. So I'm going to say molarity per second. That was the rate. Now I'm going to put in B's concentration squared, and B is, and that's on the bottom, so B's concentration is 0.4 molarity, and that is squared. I'm just going to write it twice because that's what 0.4, sorry, molarity squared is, just two of them, so I just broke that up into two. And then finally we have C, which is 0.2 molarity. A molarity cancels out with one of the molarities, and so what we have left over is a second and a molarity and a molarity. And let's just calculate that out real quick. Put that over there, put this over here. 0.04 divided by 0.4 divided by 0.4 divided by 0.2 is 1.25. So K equals 1.25, and don't forget your units here, seconds and molarity squared, so that's over molarity squared seconds. And this is your answer. You need not only the rate law expression, but what does K equal? And that is our third one.